Today we continue the reinforcement learning for animation, and we'll be looking at one of my favorite papers because it influenced the community a lot and probably led to the motion matching as we know it today, but also because it's still a lot referenced on research today because of its way of encoding the animation data and using the animation data. Hi, I'm Jerome, and today's paper is Motion Field for Character Animation, a paper from 2010. So, as usual, I will import all my libraries. I've done it before because I have PyTorch this time, so it takes a bit of time. And then I will load my character, I will load my little displacement mesh, and I will load a lot of animations. Even if I'm not actually using all of them, I'm taking a few steps in some of them, but I keep loading all of those. And I will compute the contact to know when the foot is on the ground, and I'll do it only by checking the speed of the toes, and that's it. And so that's here all the animation I have. So basically, it's all from the Lafan again, so a lot of really long take of locomotions of different style, but I'll pick a few of those at the end. So what the motion field does, it has for concept that instead of using animations, we will build a database of motion. So the way that is composed, it's basically you have a pose. Oops, that's not what I wanted to do. You have a pose, and a pose only represents the position of the character in space and the orientation of all his bones. In my case, because I have a root and a hip, so I get the two positions and I get the orientation of every bones. And then we also, for all of those poses, you also compute the velocity by doing the finite difference. So you take the next frame and you remove your current frame, and that gives you basically the delta that will allow you to say, if I'm in this pose and I add this delta, I will be in the next frame. And for the motion field, motion state is basically this. It's one pose and one velocity. So it's one pose and how much delta you will lead to the next frame. And that's how you will build the motion states. You will do this for all your frame of animations, and you just store pose and velocities as a big database. So I will have functions to compute those. So because I will have all my data inside of a big buffer, I will have a pose pack and unpack functions to easily take a buffer, returns structures as a root, hips, and quaternions, and then put that back into a buffer because it's a 4D buffers, but positions only 3Ds, the quaternions 4Ds, and all kind of stuff. So I didn't want to deal too much with that. So I just have functions that allow me to read and write inside of the buffer basically easily. I get the function that allow you to add two pose together. So a pose and a velocity, but really there's no difference between velocities or pose in this case. So it's just that add functions here, and you get the subtract function here. So that's allow you to add back the velocity to the positions. You get the subtract, that's allow you to do the opposite, of course. Then I get the lerp to be able to lerp between two poses, and I get the blending that's allow you to take X number of poses with the same number of weights and do the average sum of that pose. So all that functions that I would need later in the paper to work properly. And then I will have a function that allow me to go back into a skeleton and display my results from a pose. Now I will build my database with those functions and with a bunch of walking animations and a bunch of jogging animations, and I will just run this so I have all my states. And I pick all my positions into pack all my positions in one buffer, pack all my velocities in one buffer. Then I get the Y. It comes also later is the next frame, and I get the contacts, so all my contact informations. And see, in total, I have now 6,400 pose, states inside of my database, and that's basically 6,000 frames of animations. And I can display those, so you can see all of the poses were reset into the 0, 0 position, so they're all now relative to the identity. So I will start to be able to work with all of those states, and then I can also display what is the next frame. You know, so that's my pose plus the next frame, and then, so you can start to see that that's how we could still remember there is motions, the velocities of the root, the velocity of the hips, and all of my orientations. So, but that's all the single states that are inside of my motion field. Well, my database right now, not a motion field yet. Then what we will need with this is to be able to compute the similarity matrix. So basically trying to see how close every pose are from each other. And then we will compute the similarity weight. So how, so you get the distance, and then you get really the weights of how close the two are. And I've used a little different functions than the one that I've used in the paper. In the paper, they were only using the orientations of all the bones in the current pose and in the next pose when they integrated the velocity with it. What I will do is that I will just take the character positions of all my bones, and I will compute the velocity with the next frames. So it's matrix is a bit different, but it works the same way. So these functions allow me to receive basically a state and a velocity, and to turn that into one vector that I will start to be able to compute difference with. So I will do this for every state inside of my database, and I will compute a big matrix with a distance. So it becomes a matrix of number of states, number of positions, let's say, because that's what this becomes. You know, it becomes for every bones. I will have its position in character space, and then I will have its velocity in character space. So it's bone count multiplied by 2 and XYZ vector. And I get a big matrix out of those. And just to try to explain a little what you have now, because you have all those distance, is that you could start to compare all the distance between them. Well, you could compare the similarities of all the pose to each other, and that's you could start to think of that as a field. That's basically what they would do with a motion field. So you could try to think of representing those differences. And that's what I will do here by just reducing the number of dimensions, because, you know, the dimensions I have now is, I don't remember how many bones I have, but it's fairly big. And I will just telling, okay, try to see if there is similarities between all those vectors and turn that into a 3D representation. And that's what the UMAP allowed me to do. So we could have a kind of visualizations of the field. So what you have here, basically, every dot in this is one pose in the database. And you could see that the position they are in space is the relations they have to each other. So probably all those around there move in the same directions, are in the same pose. All the one here might be the jogging animations, running forwards, and that kind of stuff. So that's one way of representing the motion field. is just for helping. It has no true values on the representation. It's just to be able to get your head around the fact that we build a motion field, but it's a motion field in a really high dimension. So this one is just a projection of something simpler to be able to visualize it. Now, what we need is that for every pose that we will have, we need to be able to find which poses will be the closest to us. So what's the paper, basically what the paper is doing. So that's the similarity weight. That's how you compute the similarity weight. My function's over there. And then when we will try to make an animation for those, we need to be able to find the nearest neighbor of our pose. So I will be in one pose with certain velocities, and I want to find the 15 poses that are closest to me. They do an approximative nearest neighbor. I'll be lazy in my case because I don't have a lot of animations. So what I would do is that I would just drop the entire matrix here in PyTorch, and I would just do a true search using the GPU. So basically I have a function that's allowing me to get, you give him one vector and you ask him to return the k closest one, and it runs on the GPU, so it can do it fairly quickly. And the advantage of doing it in this way is that I can query one vector, but I can also query a batch at one point and request to compute that for X number of vectors at the same time, which will be handy a bit later. Now, it's all good. We have a database that is composed of all our frames. We are able to find all the frames that are the closest to us. How do we actually make an animation out of it? And that's how you have the integration functions. And what the integration function does is this one. It takes a state in which you are, and it takes X number of action. And the actions is basically for in this case, the 15 different frames I will have found. And what you do is that you average all the velocities of all the states you have with the correct weights, and the weights come from the weights similarity weights. So you average all the velocities, and then you add those velocities to your state, to your pose. So you're not adding the pose together. You're only integrating the velocities, and you move your character towards that mixed velocities. And then the reason why we had that y, and remember the next frame, is because now we need to compute the future velocities, and that we do the same. We take the average of the future velocities, that becomes our velocity. So I will get the functions to find k neighbors, and the functions to compute the new states, and I will come back to it because there is a little trick to do it after. And what we have is this. We have our character. I'll put him on spot so it doesn't go away. Come back here. What it does, it basically wanders around the motion field. So for every pose, it finds the 15 closest pose, compute the similarity weights, and blend all those weights for the velocities, and add that velocity back to this one. If you do this, only this, what would happen is basically this. We would move through the velocity field to the motion field, and at some point, hopefully we do it at some point, he might start to drift outside of the known data, because nothing forces him to stay in the motion field. All the velocities have different weights. And I would love him to start to drift. That would be great. Let me force him back from the beginning, and hopefully I can get him to drift. And so see, it starts to drift outside of the motion field because it probably reaches a point where they had no data in the field, and the velocity pushed him outside of known velocities, and it starts to blend stuff together that really are not meant to be blend together. What we do to fix this is that we will tag him with a small ratio saying, okay, you could blend all the velocities you have. It's all fine, but you will always add back 10% of the closest pose you were to. So basically, you let him walk through the motion field, but you always tag him towards an area when you know that there is data. And that's what that little 10% forces him to go back into space of the motion field where there is actual data. And then we could, just to represent it, I would slow it down fairly. Does not work anymore. That was why. Yep. On the spot, plot. And then you could display where all those frames of animations are inside of the oh, that's me. That's because of me. Where all those frame of animations are inside of the motion field. So you could see where I am and where all the pose it picked and how much it blends them. So that's a representation of what the motion field is. But as I said, it's just a representation. Don't focus on this one too much. It's just to have an idea of what the field does and how it works. And so see that ratio we have here is basically what was written here on how to compute this. You actually have to compute the next frame and then compute how from where you are, how you will, what you will be needed to do to reach the frame you know, and that's give you one of the velocities, and you integrate all those velocities back in. So, and that's what I'm doing here, while computing the velocities to reach a specific state, and then computing the new states. Basically, take the frames, take the current frame, take all the indices for all the next velocities, the weights, and then you compute the velocities that will allow you to go back in the known frames. You blend all of that together, and that gives you the new pose. And so that's how you could walk through the motion field. Now, walking through the motion field itself has no true interest, except to make a character walk indefinitely like that. What you will want to do now is to be able to control this. So being able to take our pad and make sure that we can move. And the way we will do this is basically by saying, okay, I've picked 15 different states that I can play. I have a similarity weight to know how to blend them. But if I want to get control, what I could do is that I can give more importance to one of those states. And that's what we will do. We compute the similarity weights for all the frames as we did before. And then we replace the value of that similarity weight by, so that's all normalized, but then we replace the value by a 1 for the action we want to pick. And then we re-normalize. So basically, if I go here, right now I let him do whatever he wants, but I could say, no, actually I want to play that one is more important for me, but then this one is more important, and so on and so on. And you can see that the only thing I do is that I replace the known value by a 1, and I renormalize the entire weight. So it's allow you to tug a bit more the direction for which of the 15 poses you want to pick, but not by forcing it too much. It's still using the similarity weights to blend all of those together. And then what we will have is this. So the only thing I would do here is that I try to make the character walk in the directions I want him to walk. So I will have a function that giving 2 different vectors, it returns me the signed angle distance. So I know if I know the angle and I know the direction of the angle compared to where I want to go. So that's what this function does. And my reward function for my system would just be that it has the desired direction I want to walk towards. It gets my current state and my next states. I'm not even using the current states, to be honest. And I'm just checking if basically the velocities of my next states will lead me towards the orientation I want to use. So I would get the difference between the orientation and my desired direction. And the reward is just a negative of the minus abstract. So the reward is more the penalty. If you're walking exactly in the direction I want you to walk, you get a score of 0. And as soon as you deviate, you get a negative reward. And that negativity is bigger if the bigger the error is. And so I get my pad, and what you do is, so the same thing, you take the 15 possible weights, you treat them as different actions, compute the different weights for them, compute the next states it will give you, and then compute the reward for it, and store that reward, and then you pick the best one. That's it. So I'll put him on spot also, otherwise it will start to run. So what you can see now, you get the directions, and in green you get the one it picked as being the best action it could choose, and I can start to control and see if I could walk in a specific direction. It might see here, for instance, is stuck in the 15 pose that forces him to keep running and turning. Might be able to solve that at some point, but it has the greedy algorithm. Sometimes he can turn fairly quickly, but it gets stuck and doesn't manage to leave that weird states. I managed to make it turn in the opposite way. So greedy algorithm kind of work, but of course we know it's far from being the optimal way of picking your next frame of animation. So we need to be able to use value functions and Bellman equation to go to the next system. So we'll use the Markov decision process control. And what we really have in this case, here, with the reinforcement learning part, is that we basically have a continuous state space, because my character here can truly be in any position, so that's a continuous state space. And what we have is also, because we are on that field, we have a continuous value function also. So we need to find a way to store that value function. And what we will be doing in this case, well, is using what we already have. We already have the motion field. So basically what happens is that we have, inside of that field, we have the states that are all the frames we know. And then we will compute the value functions for each of those states. So we get the value functions one value function per goal, of course. So that one will be discretized, but we will blend them together, but it will be discretized in a number of buckets for all the directions we want to cover, let's say. And then we will compute those values for every state in our motion field. And then when we want to request the value for that motion field, we will, for the value functions, we will also use the motion field to return a blended values. So if you request, that's what they've done here. You get those states. You get the next states are the three you have here, maybe, and then you will ask the motion field itself again to find all the closest value, and then to blend them back to give you the value functions again. And so it means that what we've done to find the closest pose and blend all the values with a similarity weight will be reused to also compute the value functions itself. The value functions, we will query it at a certain state. We'll find the 15 closest value to that one. And then we will use the similarity weight to blend all the values functions that we had into one value functions. So, and for the training of that value function, what we'll do is that we will do a fitted value iteration. Why? Because we only work on the states we know. So what will happen is that we will compute the next states of every state we have, and that's it. We'll stop there. We don't do explorations and all that kind of stuff like we were doing in other papers before. We pre-compute all the states and all the next states and all the actions we can take, and we compute the score, and then we iterate through that until we have the value functions that converge. So what I would do is that I will pre-compute first for all of my states the 15 actions they can pick, and where for those 15 actions, I will compute also what happened if I picked action 1, action 2, action 3, action 4, and so on. And I will compute the positions where those 15 will be. And from those, I will compute the 15 closest states that can be used to compute the value function. So that's why you pre-compute this, is because for every action you pick now, you take the 15 closest poses, you blend towards those 15 poses, and for those 15s, you retake 15 times the closest values. So we will pre-compute this to win sometimes, and I will even, I will just store it because it takes me 10 minutes to compute all of those. And now that I have all those states, I have everything from here to the next frame and all the stuff I can blend, I can start to compute the value functions. And I would do it with PyTorch because, everything is pre-computed. It's one big buffer. Everything can be done in parallel. So let's do that on the GPU so I can win a lot of time there computing that value functions. And how I would do this, it's basically, I have my value functions that is just a bunch of zeros to start with. I'll put on the GPU my deltas of how much each of my frames will rotate. I get the indices of the next frame to look at the value functions, and I get the weights. I can compute in one go the offset of orientations that would happen for all of my states at once. I have a bunch of walking animations and a bunch of jogging animations. So I just have a flag to know if I'm walking or jogging. And then you compute what will be the next orientations for all the states for all the states for each actions and for each offsets in which I wanted to look at. You compute the rewards, and basically the reward is the same as before. It's the negativity of the absolute next orientation. And I'm also adding a score depending if I'm walking or jogging, because I only want to have one value function that make me walking and one value function that will make me jog. And then basically that's where the blending happens. So how to say? You get a 2D blending in this case. What happens is that you will blend the 15 values. You have to blend them with the weights, and then the orientations in what you want to work. I've said that I've split the values in X numbers, and then you will just say, okay, if my value is here right in the middle, I just need to do a linear blend between those two values. And so that's what this part is doing. It's checking where you're landing in the orientation, and you just take it gives you the range of the two values you have to blend, and with which blend factor you have to blend them. So that's what this is computing. All of that is pre-computed once into one, a bunch of big buffers, and then at every iterations now, every epoch, you basically take all the next value functions you gather using all those indices, all the values together, you blend them, you compute the next one, and then you get the usual value functions. Your Q is the reward plus the expected next reward, and your best value is the maximum of all the possible functions you have. Then I compute the Bellman residual to see how much the current value functions compare to the expected value functions is, and that's for you to see if you are actually converging. And then when you finish, I put that back on the CPU. And I compute that twice, so I will have two value functions. I get a value functions for the walking and one value function for the jogging. So basically, that's what this score will be. It will give you an advantage of walking when I ask you to walk, and an advantage of running or jogging when I ask you to jog. And I compute those two. So I get 300 epoch to try to get that stabilized, and I get the gamma of 0.99. And we could see now the convergence of the jogging one. So that's the amount of difference I had in the value functions and the expected next values. And so what you have now with this value function is basically that we could start to use it as we use it usually. So what I have is I only have one button to decide if I want to use the value functions for walking or the value functions for jogging. I got the direction in which I want to walk. I compute my 15 closest neighbors again. Then for all of them, I compute the next pose. And what I would do is that I will store the query inside of what I call a batch query, because I will store for the 15 of them, I will store the positions where that would lead me. And I will store the batch theta prime also, so how much basically score that will give me. And then I can re-request the next indices and next weights, but for the batch now. That's why I said it was useful in PyTorch to be able to say, I want to query the system for one query, or I can query it for a batch of queries. This is what allowed me to query the 15 different positions at once. And once you have this, what I could do now is compute the future reward for each of those 15 different poses. And I get the future reward. And then I use that future reward to know which one of the value I want to use. Then I also use the contact of my foot. And I've been lazy in this one. I'm only checking if the toes are in contact or not. And if they are in contact, I'll lock them in positions. And if they're not, I'll let them go and blend them back to their default positions to the animation slowly. That's it. And I don't do anything more fancy on the foot contact and so on. And that gives you the motion field. So I will not put him on spot this time. Give him some room, and here we go. Now, to be honest, I had to cheat and slow down a lot the rendering and to speed it up again in a post. And that's only because I guess it's my PyTorch implementations. Calling PyTorch twice a frame probably forces the entire system to go to synchronize the CPU and GPU and drop my frame rates pretty badly. So this is speeded up, and that's only speeded up because of my PyTorch implementations. This was the motion field, and as I said, is one of my favorite paper. Always wanted to implement that one. Finally had the chance to look at it, which was really great. I hope you liked it, and see you next time.